Okay, so on exam 1, let's see. The problem that people lost the most points on was number 2. So this was the one that said this vector u is equal to x, xz, y cosine of xz. And you want to calculate u dot expressed in terms of x, y, z, and then x dot, y dot, z dot. Okay, so let's just break it up into the, we're just going to take the time derivatives of each of the 3 components. So d dt of x is, just dx dt. So most people got this one right. And so in terms of these things, you'd express that as x dot. The next one, d dt of xz, is from the product rule, dx dt times z plus x times dz dt. And so that's, you can express that as x dot z plus xz dot. And then the last one, d dt of the quantity y cosine xz. From the product rule, this is d dt of y times cosine of xz plus y times d dt of cosine xz. So this one here is just y dot, so I'm going to just keep simplifying this little by little. So we have y dot cosine of xz plus, so now we have y times the derivative of this. But this has some chain rule stuff, some product rule. So the first thing is let's deal with the chain rule because you have this xz inside our cosine function. So for that, we're going to go negative sine of xz. That's the derivative of the cosine function with respect to what's inside there, times d dt of xz And I forgot to multiply by the y here. So I'm just going to put the y there. We still have the negative from the derivative of the cosine. Okay. Any questions so far? Now the last thing we have to do is just this thing. And that's just going to be dx dt times z plus x times dz dt. And so altogether, this third component comes out to be y dot cosine of xz minus y times the quantity x dot z plus x z dot times sine of x z. Okay. Most people, did the first one a few more people made mistakes on the second one, and then a lot of people made a mistake or two on the third one. But that's how to think that one through. Anybody have any questions about that one specifically? And so then the answer as a vector is just those as components. So you got x dot for the x component, x dot z plus x z dot for the y component, and then that ugly thing, y dot cosine of xz minus y times the quantity x dot z plus xz dot sine of xz for the z component. Okay. Anybody else want to see any other problems? Yeah.
Do number 3.
Sure. So number 3 is one of these relative motion problems. You have this at an angle of 45 degrees with the horizontal. And then this is perpendicular to that first member. Oh, that's 4. Okay. Thank you. So number 3, that one says you have a velocity vector, and it's given as a function of z, cosine z, sine z, z. Okay, that's the velocity vector. And on these, we're always, assuming that the position vector is this. Okay, well, that means that cosine of z is dx dt, because that's the definition of the velocity vector. I'm just using the definition of the velocity vector, that it's equal to dp dt. This is dy dt. And this is dz dt. Okay? The acceleration as a function of z, well, let me just write it generally first, and then we'll think about what's functions of what. This is going to be dv dt. Okay, that's the definition of the acceleration. But since we don't have v as a function of t, we're going to have to use the chain rule. We have v as a function of z. So you can think of this as d dz of this function v of z, and then times dz dt. Okay. Well, now we can take this derivative of v as a function of z. D cosine of z dz is negative sine of z. D dz of sine of z is cosine of z. D dz of z is 1. And now we're multiplying that by dz dt. Well, that's just the z component of the velocity. So this. And so now we have the acceleration given all as a function of z, and it's equal to negative z sine of z, positive z cosine of z, z. Okay, any questions about that one? One thing, it definitely wasn't like a deal breaker on this problem. There were people who got all the points on this problem and used like a standard coordinate system. But on number 4, so that's the one like this, and you're given rotational quantities, angular quantities, and you have to calculate the acceleration of this point P. You could have made your life easier by choosing a coordinate system that somehow lines up with this. Some people chose this to be the x-axis and this to be the y-axis. Some people chose the y-axis to be pointing along that member, and then the x-axis would be opposite the way I have the y-axis. Either of those make the vectors pretty simple to calculate. But yeah, I mean, you could do it with cosines and sines of 45 degrees and stuff, and it works perfectly fine. But this was a bit of a time saver if you noticed it. Any other questions on the test? Okay. Any homework questions? Yeah.
Do like question 8 on the article.
I hope so.
I think I just forgot how to do that.
Particle kinetics. Number 8. Oh, yeah. So this is a chain rule one, but it's the kind that you prefer not to see because you're not given the velocity as the function of the parameter. You have to get there. And okay, so let's draw what we can. So we know it's moving along this parabolic path with a speed of 8 meters per second. So it says that the position is parameterized by x, like this. If you want to draw that, it's moving along this path. It doesn't say which direction it's moving along the path, and you can't do these problems without knowing that, so I'm going to say it's going this way. But really, the problem should say that. Okay, so what we need to, so the speed is 8 meters per second. And what we need to do, since we have this parameterization, we have to come up with a velocity vector in terms of that parameter. So the way to do that is we can find a unit vector that's tangent to this path at any x. I'll call it u. You know, this is tangent to the path. By taking a derivative of this vector with respect to the parameter. So that's, you know, dx is 1, dx squared dx is 2x. But that's not a velocity vector. That's in the same direction as the velocity vector. If this problem had specified that this thing was moving the other direction, that would be in the direction of decreasing parameter, and we would have to multiply this by -1. Okay, you can probably imagine, like, if we want to imagine the tangent direction at this point, if it's moving this way, it's going to be tangent like that, you know. If it's moving back the other way, it's going to be the exact opposite vector going this way. So that's where that negative would have to come from. Okay, but so we have something that's the direction of the velocity vector, but it's not the velocity vector. We have the speed, but we can't just multiply the speed to this because this has some unknown length, you know? So if this has a length of if this has a length of 3.6 and you multiply 8 to something with a length of 3.6, you don't get something with a magnitude of 8, you know? You get something with a magnitude of 27 or whatever, you know? So what we have to do is first find a unit vector in this direction, and then we can multiply by 8. And then we have something that's in the direction of the velocity and has a magnitude of 8. In other words, it's the velocity vector. So the unit vector in the direction of the velocity is each of these divided by the length. Okay, so what's the length? It's 1 squared plus 2x squared square root. And so this tangent vector is 1 divided by that square root. And then 2x divided by that square root. And now, since that has a length of 1, the velocity vector as a function of x is equal to both of these times 8. So I'll write this as 8 times 1 plus 4x squared to the negative 1/2. And the y component is 16x times 1 plus 4x squared to the negative 1/2. And these always get ugly. The least ugly kind of problem that I've found is helical motions, but even that, I mean, it's always uglier than if I just give you the velocity in terms of some position variable. But that's all right. So the acceleration is going to be equal to dv dx times dx dt. So this dv dx is going to get complicated looking. Don't forget that when we're done, we also have to multiply by dx dt. And this is dx dt. Okay. This one is dy dt. That doesn't come up in this problem, but that's just using the definition of the velocity vector. Okay, so dv dx is equal to -1/2 times 8 times 1 plus 4x squared to the -3/2 times 8x. That one wasn't so bad. The y component, you have to use the product rule. So we have 16 times 1 plus 4x squared to the -1/2 minus 1/2 times 16x times 1 plus 4x squared to the -3/2 times 8x. And then multiply that by dx dt, which is 8 times 1 plus 4x squared to the -1/2.
Thank you.
Sure. So if you don't waste a lot of time, spend a lot of time simplifying it, then I guess it's not horribly long, but it's sort of a product rule, chain rule kind of workout.
And then for this problem, they wanted the net force when x was at 2 meters.
Oh, okay. Okay.
So you just plug x in and then multiply by.
So, yes, that's right. So once you have that whole expression, then plug in x equals 2, and that might not actually be so bad. Is it going to be? Yes, a little bit. But so plug in x equals 2, and that'll give you the acceleration at x equals 2. And then from there, what did you say, net force?
Yeah.
So then Newton's second law just says that the net force when x is equal to 2 is the acceleration that you got times the mass. Dang it! Well, maybe it said the mass is 1. Probably didn't.
I think it was like 30 or something.
Yeah. Any other questions about that one? What's the acceleration? Let's do this. Nobody asked, but what's F net at x equals 0? Well, that one's pretty easy to do. So when x is equal to 0, dv dx. So let's solve for that. Everything in the x equation is multiplied by x. So x equals 0 is going to make that go away. for the y component, everything in this second term is going to go away because you're multiplying by 0, but the first term isn't. So this is going to be 16 over the square root of 1, so it's just going to be 16. Okay. Dx dt is this thing. The stuff in parentheses is 1, so 8 over the square root of 1. So this is going to be 8. And so the acceleration at x equals 0 is 0.16 times 8. So that is 128. Okay, does it make sense that we have an acceleration when x is equal to 0 that's up? Yeah, it does, because since the speed isn't changing, there's no acceleration tangent to the path, right? That would make the speed change. So all you have is basically, you can think of it as like a centripetal acceleration. Like imagine here that this is part of a circle. You match a circle to exactly the curvature at that point, and it's going to be going straight up. Okay, so when x is equal to 0, that makes sense. It doesn't make sense anywhere else, because that it would be perfectly vertical, because it's always going to just be perpendicular to that path. But if the speed isn't changing, that acceleration always has to be just perpendicular to the path. And now that you have that, F net at x equals 0 is the mass of 3 times 0, 128. So that's, what am I doing? 300. 0, 384. Okay. Any other homework questions?
Yeah, number 10 on vertical units. I was here confused by what they meant by the power vectors.
Let's not keep up this charade anymore. It's not them, it's me. I wrote these problems. I can't hide behind some other doofus any longer. Okay. So it's a carousel. It has a radius of 2.2, constant angular velocity. Okay, so I'm going to think of it from above. I'm going to use a coordinate system like this. I'm going to choose a location for the kid. So this is 2.2 meters. I'm going to choose the kid's location to be here. I don't know why, but I am. So just straight in the negative y direction from where I put the origin. And what was the angular velocity? I have it here. It's just going to make my computer crash. 5 radians per second. It's a constant angular velocity. It doesn't tell the direction, but what you would find is with a constant angular velocity, all the answers would be the same no matter which way you did it. So I'm going to think of it as counterclockwise, so it's positive. And Okay. The kid has a mass of 20 kilograms. So the first thing we have to do is calculate the acceleration. The z-axis is coming out. This is just a circular motion thing. So if I call this p, the acceleration of p is the watermelon equation. Alpha is 0, it's a constant angular velocity. Omega, the way I drew it, is 0, 0, positive 5. R, where I drew it, is 0, negative 2.20. And so the acceleration of this kid is 0 plus 0.005 crossed with the quantity 0.005 cross 0, negative 2.20. And if you plug that all in, you get 55 in the 0.550. Okay, so there's his acceleration. Any questions about that? Sometimes people get a little turned around on like, so now we have this physical thing and gravity is acting on this kid. And so I think sometimes people get a little confused on what gravity does and doesn't do with accelerations, because the first time in physics that you talk about gravity, you see it as an acceleration for things in free fall. But remember, gravity doesn't produce an acceleration. It produces a force, okay? And so this kid is moving in a circular path. These are the things that define that circular path, and so this is the end of the acceleration. Okay, so, all right, so what's the net force now? F net is just going to be equal to the kid's mass times this acceleration. So that's probably 0, 1100, 0. But now we have to think about the individual forces. So now we're going to draw a free body diagram. And really the only thing that matters to us is, so let's think of the kid here, and let's think about the coordinate system for a second. This would have y pointing this way, x pointing towards us, and z up. Okay, so like in order for us to see the kid like this, in this position, we'd have to be looking down the x-axis. Do you see that? Okay, so he's growing up before our eyes.
Still doesn't have arms.
Yeah, right. Okay, so what forces are acting? We already know the forces going on in the XY plane. Okay. But what about the Z forces? There's a weight force that's equal to 20 times 9.81. So 196.2. And then there's a normal force like this. Okay. And so if you think of Newton's second law in the z direction, what we have is negative 196.2 plus n is equal to the z component of F net, which we already figured out is 0. Okay? So the normal force is equal to 196.2. Okay, well, the total friction force is the magnitude of the x and y forces. That's the only thing producing forces in the xy plane. So that is, 0 squared plus 1100 squared square root, which obviously just gives you 1100 back. And so F total is equal to the coefficient of friction times the normal force. So we have that 1100 is equal to the coefficient times 196.2. What's 1100 divided by 196.2?
I got 5.6, which also confused me.
5.6, okay.
That's certainly fine.
Yeah, well, so normally you don't see coefficients of friction bigger than 1. There are materials, combinations, pairs of materials that give you coefficients of friction higher than 1, but I've never seen one as high as 5.6. So basically, like, it's impossible for this kid to stay on using just friction, That's,
Just hold on.
yeah, just hold on. But we had to assume that this kid is not holding on. But
He has no arms.
that's true. He has teeth, though.
Yeah, and a big chin.
Yeah, big chin.
And hold on to his chin.
Okay, so anyways, that's how you do it. That one takes a little bit of thinking around physically, like what am I trying to get at, It might be the only one that I make you do that kind of stuff.
The contact force is the combined normal force and friction force?
Yes,
Okay.
that's right. So it asks for that. What's the,
Part A. What's the contact force vector applied to the child by comparison?
yes, that is right. So the F contact is the force of friction plus the normal force. So that's the friction, or so the normal force is in the positive z. So we got 0, 1100, 196.2. That's the contact force. Any other questions about that one? Any other homework questions? We might as well just, yeah.
I have a really quick
Yeah.
question. On question 9, I think it is.
Yeah.
Is it supposed to be acceleration in meters per second, or is it radians per second per second? at the very end.
Oh, you're right. That should say radians per second squared.
Okay.
Yeah, it's an angular acceleration. Oh, and that one, you have to sort of think the same way on that one that you have to in number 10.
Okay.
You have to think about like, okay, now what's the normal force? Can I take this net force apart and figure out what individual forces are? But start out by doing the circular motion stuff, calculate the acceleration, multiply by the mass to get the net force, and then start thinking about individual forces after that. What number did I assign up to? All of them yet?
15.
Oh, that's everything. Well, we didn't really get to anything today, so I can't really assign you anything new. So that's good news, I guess. So next time we'll talk briefly, quickly about general. So now we're moving on from individual particles to collections of particles. Okay. So let's just get this in your notes. So we're moving from individual particles to collections of particles. Well, there's one important thing that we're going to be able to say about general collections of particles. So you can think of that as just blobs of stuff, you know? But, you know, think of just this blob of stuff flying through space. We can say one interesting thing about it. Newton's second law still holds, no matter what the connection is between these things, whether it's a blob of pudding or it's a bag of marbles that's just thrown everywhere, you know. It's kind of amazing that you can say anything meaningful about both of those two things. But what you can say is that F net is still equal to the total mass times the acceleration of the center of mass. It's kind of surprising we can even say that. But if these collections of particles are organized rigidly into a rigid body, you know, if this collection takes the form of a rigid body, we can say two things. Newton's second law holds. So F net is equal to the mass times the acceleration of the body's center of mass. And the moment equation we can talk about now. I'm going to call this rotational Newton's second law, but this is the moment equation. And this says that the net moment about some point A is equal to the mass moment of inertia about A times the angular acceleration vector. What A can you use? What about point can you use for this? In statics, we spent all of statics building really bad habits about this, because in statics, you could choose any point you wanted and the moment equation held. In this case, this only holds as long as A is either, so you have two options. The center of mass of the body, or a point fixing the body to the coordinate system. So this would be like a hinge or a ball and socket joint or something. Okay, so I'll talk briefly about pudding dynamics. That's how I think of it. It's just like blob. What can you say about blobs of pudding flying through space? You know, not very much, but a little. But you can say a lot if you freeze the pudding and it's a rigid body, you know. And that's good because in outer space, pudding freezes, obviously. Okay, that's all. So no homework. Live it up.
So we're just always reviewing homework problems we can build.